Hello, I'm Anand from Sandbox AQ, and I would like to present joint work with Antoine Jou on solving certain multilinear equations. We need a couple of definitions before phrasing the problem, but let's begin by staring at a very familiar definition, that of singularity of square matrices. So given a square matrix, it's singular if there is a non-trivial kernel. And I'm going to phrase this slightly differently and say that it is singular if there is a pair of vectors where one is in the left kernel and one is in the right kernel. Right? So this is equivalent. And now I'm going to phrase this perversely, but still in an equivalent way, and say that the square matrix is singular if there is a pair of vectors such that both the vectors are non-zero. And if I multiply the matrix by all but one of the vectors, then the resulting vector is the all-zero vector. Right? So this is a very strange way of saying something that is very obvious, but it is one that generalizes. So for three-dimensional tensors, we call them singular if there is a triple of non-zero vectors, such that if I multiply the tensor, with all but one, so two of the vectors, then the resulting vector is the all-zero vector. Okay, why bother? So the main problem that we will study is given a tensor to find a solution, which is a triple of vectors, such that if I multiply the tensor with two of the vectors, then I should get the all-zero vector. Right? So we are finding a singular point. Okay, so this actually generalizes to more than 3 dimensions. And I'm actually going to write this down in rather tedious notation because it's hard to picture what it means to multiply a tensor by 2 vectors, so I don't want people to get confused. So it's good to have something concrete. So we're going to allow arbitrary dimensions, let's say r plus 1 dimension, and we're going to work over a field. Think of just complex numbers for now. And a tensor is going to be an element in the tensor product of a bunch of dual vector spaces. And we are going to allow the vector spaces to have different lengths, right? So they don't all have to be the same length. And so this is just a fancy way of saying that A is a multilinear form. That is, it's going to take an r plus 1 tuple of vectors and give you a scalar, right? So if you substitute or evaluate it at the r plus 1 vectors, you get a scalar. If you evaluate it at just r, which is 1 fewer than r plus 1, then you're going to get a vector. And so this plays nicely with the previous intuition that we had. So the question is to find a tuple of vectors, each of them non-zero, such that if I evaluate this multilinear form at all but one of the vectors, then I get the zero dual vector. So this is the formal problem we're solving. Don't worry about the notation. The previous intuition was perfectly fine. Although there is one useful thing here, and that is that if I take a solution, and if I look at a vector in a solution, and I scale it by multiplying with a scalar, then that's going to remain a solution, and it's in some sense the same solution. So we are really dealing with a tuple of projective vectors as the solution. And so from now on, when I say a solution, I will think of them projectively, right? So I will identify those that are the same up to scalar multiplication. Okay, so in the 2-dimensional case, when do you know if a solution exists at all? And the answer is rather familiar. It is precisely when the determinant vanishes, right? And remarkably, Cayley wrote down an expression that is a generalization of the usual determinant for the 3-dimensional case for the simplest tensor format, namely 2 by 2 by 2 tensors. And like the determinant, it is a polynomial in the entries of the tensors. It's actually a homogeneous polynomial with integer coefficients, and it vanishes precisely when this 2 by 2 by 2 tensor vanishes. And this field lay dormant for forever until it was revived by Gelfand, Kapranov, and Zelvinsky in the 90s. who extended Cayley's construction to arbitrary dimensions. And the only constraint is that the lengths of the dimensions have to satisfy the property that if I take the length of the longest dimension projectively, so K0, then that can't be bigger than the sum of the lengths of the other dimensions, projectively again. Right, so this is just saying that one of the dimensions of the tensor cannot be skewed to be so large that it's bigger than the sum of the others. And this is a fundamental constraint, so this is not an artifact of their construction. So as long as this constraint is satisfied, they give a definition for hyperdeterminants, which vanish precisely when your tensor is singular. And to make sense of this constraint, think of the two-dimensional case. So all it says is that the left dimension is at most the right dimension, and the right dimension is at most the left dimension. So all you're left with are square matrices, and tensor formats generalizing square matrices are precisely the ones for which the hyperdeterminant makes sense. Okay, so that seems nice. Okay, so the question is, are hyperdeterminants in more than two dimensions hard? Or is it easy like determinants? And the conjecture is that hyperdeterminants are hard. So in some sense, in complexity theoretic sense, they behave like permanents and not determinants. But a proof remains elusive. And in the very same paper, they identify some of the shortcomings of known techniques. Once again, I will make sure I don't time out. Yeah. And so our major contribution in this paper is a reduction from homogeneous multilinear systems to hyperdeterminants. Right? So you can think of it as evidence for hardness of hyperdeterminants, which is sort of our true motive. Or you can think of it constructively as a means of solving multilinear systems using hyperdeterminants. So what is the minimal model for hyperdeterminants one can think of? It is some kind of a black box that, given a tensor, throws out the hyperdeterminant value. Sadly, we don't quite know how to exploit such a black box, but we require a white box, so we need an arithmetic circuit. So given an arithmetic circuit that computes the hyperdeterminant, we can build one that solves homogeneous multilinear systems. But there is a small qualifier in that the homogeneous multilinear systems that we solve have to be generic. What that means is that it can have at most one projective solution. And there's a theorem of Wyman and Zelvinsky, which says that most systems are generic. So in some sense, we are solving. So the word generic is appropriate here. Okay, so how do we do the reduction? And there are two ingredients. So if you're trying to solve, oh, one second. It's trying to time me out again. So if you're trying to solve a linear system and you want to do it through determinants, then you look to Cramer's rule, right? And Gelfand, Kapranov, and Zelvinsky proved an analog, which will be the mainstay of our reduction. And we will also use an arithmetic circuit technique by Bauer-Strassen, which takes an arithmetic circuit that computes some polynomial and computes all its partial derivatives using an arithmetic circuit of roughly the same size. Okay, and we will see shortly how all this works, but I also want to mention that our reduction also works for quantum circuits. And this is interesting because hyperdeterminants, at least Cayley's formula, was rediscovered by quantum physicists as a measure of multipartite entanglement. So they are of relevance for quantum computers. So one may be curious how hard hyperdeterminants are on a quantum computer, and our reduction says likely hard. So one caveat here is that we only solve the multilinear systems approximately because I don't quite know of a quantum version of Bauer-Strassen, but we can have an approximate partial derivative computation using the quantum Fourier transform. Okay, so what remains is probably the main open question. Can you reduce your favorite hard problem to solving generic homogeneous multilinear systems? For that would resolve the hardness of hyperdeterminants. And my hope is yes. Yeah, let's see how it goes. Okay, so on to the reduction. So someone gives you a tensor and wants you to solve the associated multilinear system. So the first thing you do is you have at hand an arithmetic circuit to compute the hyperdeterminant. So you compute the hyperdeterminant and see if it's 0. If it's not, then you say, okay, there's possibly no solution. So you reject it. And if it is, then I'm going to assume that A is a non-singular point of the hyperdeterminantal variety. And I'm going to tell you what that means in a moment. So don't worry. It essentially says that determinant A of A is equal to 0 says there is a solution. And the second constraint says there is just one solution. Okay, so don't worry about it. So I can give this unique solution a name, which I've done here by writing it as a bunch of vectors. And the theorem of Gelfand-Kapranov and Zelvinsky is going to relate the coordinates of this vector, which we seek, to hyperdeterminants in a beautiful way, right? So the way they do that is they look at a tensor, which I'm calling X, of the relevant format. And I'm going to think of this tensor as being made up of commuting indeterminates or variables. So I'm just thinking of the tensor entries as variables, like nothing fancy. So then the hyperdeterminant of this tensor is a multivariate polynomial. So it makes sense to ask about the partial derivatives of the hyperdeterminant with respect to one of the tensor entries. Right? So that'll be again, so this will again be a polynomial. So once I have that, I can evaluate it at A, which is the tensor, right? And I would get a field element. And Gelfand-Kapranov and Zelvinsky say that this field element is related multiplicatively to coordinates of the solution that we seek, with each vector contributing one coordinate to this product. Right? So this is beautiful, and this is an analog of Cramer's rule. Although it's hard to identify it as such because it's written under the Segre embedding, which I won't get into. So we started out with a polynomial system, and we again have a polynomial system. So have we made any progress at all? One thing to note here is that A being a non-singular point merely means that there is at least one tensor entry with respect to which the partial derivative at A is non-zero. That's all it means, right? So there is at least one tensor entry which we can find by just enumerating all these partial derivatives, and it is non-zero. And by Gelfand-Kapranov and Zelvinsky, this implies that the corresponding coordinates that appear as the product are all non-zero, right? Because otherwise the product will go to 0. So the key observation here is that this allows us to identify one coordinate in each of the solution vectors as being non-zero, and then we can normalize them to be 1 and try to figure out the others. But the moment you do the normalization, the others are easy to read out. All you do is you take the partial derivative, wherein the coordinate that you're interested in appears, and the other coordinates are ones that you've already set to 1. Right? So you can just read off from the value of the partial derivatives. So this is the reduction. And where does Bauer-Strassen come in? It helps to do the reduction without blowing up the circuit size, because all the partial derivatives that you seek to locate the non-zero coordinates and to read off the other coordinates can be computed in with an arithmetic circuit, roughly the same size, maybe 3 or like 5 times the size of the one that computes the hyperdeterminant. Okay, so that's our reduction. As I said, I think of it primarily as evidence towards the hardness of hyperdeterminants, but you can also use it constructively, in that you can solve multilinear systems faster than previously known. So a few examples are listed here. And the tensor formats for which this works, once again, to make sure I don't get timed out again, are called boundary format tensors. And these are the ones that satisfy the inequality that I keep harping about with equality. right? So these are tensors that are true generalizations of square matrices. What happens here is that I'll illustrate it with an example. So if I take a 3 by 2 by 2 three-dimensional tensor, then its hyperdeterminant can be written as the determinant of a usual square matrix. And if you choose the basis nicely, then the entries of this square matrix are just going to be zeros or the tensor entries. Excuse me. So on the right, you have the usual determinant, which you can compute, right? So, so this gives you a way of computing the hyperdeterminant of boundary format tensors, and therefore through a reduction for solving multilinear systems. What is the complexity of this? Well, so this recipe, again, is thanks to Gelfand, Kapranov, and Selvinsky. What happens is that on the right, you get a square matrix whose dimensions are equal to the degree of the hyperdeterminant times the degree of the hyperdeterminant. And usually, the degree of the hyperdeterminant can be exponential in the length of one of the vectors, or worse. So, apologies again. So what's on the right is a huge matrix. So don't always expect like fast polynomial time algorithms for boundary formats. But there are some special cases where you get pretty nice results. For instance, you get sub-exponential complexity for these three-dimensional boundary formats. And for certain formats relevant to quantum computers, you actually get quasi-polynomial time. Okay. With the time that is remaining, I want to talk quickly about hardness of hyperdeterminants modulo a prime. So far, we've been sort of trying to derive hardness through purely complexity theoretic reductions. Now I will try to do so using some cryptography. And before discussing about the hardness, I have to say that we have to replace the complex numbers by a finite field now. And the way hyperdeterminants are defined is very geometric using projective duality. So things like tangents, like Gauss map, these things show up. And some of these need taking partial derivatives. And these don't work well once you have finite fields, right? But in this very special case, Kaji proved that hyperdeterminants over finite fields make sense. So we can use that theory to try to derive hardness results for hyperdeterminants modulo a prime. And to this end, we are going to look at what's called the tensor isomorphism problem. This has been of great use in cryptography very recently. And the problem is fairly straightforward to state. So you have a tensor, and you have a triple of invertible matrices of the right dimensions. And you multiply your tensor in each of the dimensions by these three matrices, and you get another tensor of the same dimension. And these two tensors are deemed to be isomorphic. So the question is, given two tensors, are they isomorphic? And if so, find an isomorphism, which is a triple of these matrices that takes one to the other. So this is the tensor isomorphism problem. And there is a close-knit reduction of some familiar problems, some new problems. And a lot of these have found cryptographic applications, and at least three of them are foundations of very recent post-quantum signature schemes that were submitted to NIST. So it would be nice to try to derive hardness of hyperdeterminants from the tensor isomorphism problem. We don't quite know how to do that, but instead we will derive hardness from a pseudo-random assumption that underlies one of these cryptographic systems. So instead of a purely complexity theoretic assumption, this is like an average case cryptographic assumption. So the assumption says that if I take a random tensor and a random triple of invertible matrices, right? So that will give me a pair of tensors that are in the same isomorphism class. And the assumption is that this pair is computationally indistinguishable excuse me, from a pair of random tensors. And again, we don't quite prove that this problem reduces to hyperdeterminants modulo pre, but we prove a very closely related problem does. And the closely related problem replaces the three invertible matrices with matrices of determinant 1. So instead of GLN, we have SLN action. And here, the easy part is that hyperdeterminants are invariants of the SLN action. So two things that are isomorphic will always have the same hyperdeterminant value, right? So if it's in the first distribution, the hyperdeterminant being equal tells you they are. And surprisingly, the hard part is proving that if I take two random tensors, then the hyperdeterminants are not the same, right? You would expect this heuristically to happen with probability 1 over p. But hyperdeterminants have large degree and are very complex polynomials. But using certain effective Langway bounds, so these are just generalizations of Schwarzschild lemmas, where we also use the fact that the hyperdeterminant has only one component, so we get slightly better bounds. That if I take two random tensors, then with probability roughly 1 over p, they are different, right? And so it would be nice to do the reduction with GLN instead of SLN. And I think it's plausible because there are some prior work in cryptography that we can try to mimic. And I think at least for small p or fixed p, they should work, but it's still in progress. How am I doing on time? Very poorly, so I think I'll stop here. And in person, I'd be happy to take some questions. Thank you.